In this video, we're going to talk about a special kind of series, which is a telescoping series. An example of a telescoping series is any series where as I continue to add more terms together, so I see this one minus a half plus a half minus a third plus a third minus a fourth, what is happening is the more terms that I write, it's eventually going to collapse down to just a few terms. So if you look at that one, what happens is the half cancels, the third cancels, and then if I continue writing, more terms would cancel, and it would allow me to predict what the sum is if it is indeed a telescoping series. So we're going to look at one way to find the sum of a telescoping series, which is to expand and then see what terms are canceling and determine the sum that way. There's a more complicated way, which is to identify the pattern and write a limit, but that's more calculus based, and we'll save that for when you're in that course. So if I'm looking here at this first problem, so I'm looking at the series of the sum from n is 0 to n is infinity of 1 over n plus 1 minus 1 over n plus 2. Anytime you're trying to determine the sum of an infinite series, you first need to know, well, does it converge or not? Well, the first thing that I do is I determine whether or not it passes the nth term test or not. And so I'm going to evaluate the limit as n approaches infinity of the expression that's here on the inside, 1 over n plus 1 minus 1 over n plus 2. And what that gives me is as the size of n increases, 1 over n plus 1 is approaching a value of 0. And 1 over n plus 2, as n continues to get bigger, is approaching a value of 0. So this is equaling 0. Now the nth term test just tells me that if that limit did not equal 0, it would diverge. So the nth term test is conclusive or inconclusive. So we don't know if it will converge or not. Now, a way to tell that is to tell if the sequence of partial sums converges by looking at the graph of the series of partial sums. And so start by looking, I have the sequence plotted here in Desmos, and we're looking, and at first we're just plotting the sequence of terms, which is the nth term test. And as what you see is, as I start to increase the size of n, my values of my terms are approaching that of 0. So the nth term test basically is inconclusive because the limit does equal 0, so we don't know if that series will converge or diverge. And so I'm looking here at my series or my sequence of partial sums here, and I'm looking at, well, what is happening to my sums as I increase the number of terms? And what is happening is, as you increase the number of terms, your sum is approaching a value of 1. So does it appear to be bounded? The graph of the sums, yes. It converges. And we predict that it converges to a sum of 1. Now, the way we could find this without looking at the graph is we would start expanding the sum. So what I do is I start by putting in this number for n and writing down what I get. So I'd have 1 minus 1 half. And then my second term be plus. Then we increase the size of n by 1. So I'm putting in 1 for n this time. I get plus a half minus 1/3. Now plus, and then I keep going with this. And so I'd say plus, increase the size of n again, so I'm putting in n as 2. That gives me a third minus a fourth. And then this pattern would continue on. Now notice what's starting to happen. So I've already, through the process of expanding, I have the halves are going to cancel. The thirds are going to cancel. And if I continued on, let's do one more term. And so we just finished putting in 2 for n. Let's put in 3 for n. We'd have plus a fourth minus 1/5. And then you see that the 1/4 cancel. And so what's happening is things are starting to cancel. The more terms I add, the more things are going to cancel. And all that's left is that first number that did not cancel at. And so we can get the estimation of the sum this way to be 1. All right, let's look at a couple more examples. So I want to determine if the following series will converge or diverge. And if they converge, find the sum. So the way you start is you do the nth terms test. So I'm going to find the limit as n approaches infinity of the expression that's on the inside, which is 1 over 2n plus 1 minus 1 over 2n plus 3. Now, and I can do this graphically when I graph it and see if the graph is going to the x-axis, or I can do it by just logistically looking at what's happening as I increase the size of n. As I keep increasing the size of n, 1 divided by 2 times n plus 1 is approaching a value of 0. And then minus 1 over 2 times n plus 3, as n continues to get bigger, this value becomes 0 as well. So the limit equals 0, which means that the nth term test is inconclusive, which means that I don't know if it converges or diverges. So if it's inconclusive, we have to do something else. Well, the other method that we have is to see if it's a telescopic series. Now, we really don't know if it's a telescoping series until we start writing out terms. And we can assume that maybe it is when I see two fractions subtracting from one another. So let's start writing out terms and see what is happening with my expansion. So I start by putting in 1 for n's and write down what I get. So I end up with, I have 1/3 minus 1/5. So that's my first term. And then plus, now I put in 2 for n's. We have 1/5 minus, putting in 2 for the n here, that's 1/7. And so we look, and already the 1/5 have canceled. And then I continue on and say, all right, let's go another term. So that was when n was 1. This is when n was 2. Let's do when n was 3, and continue on. So when I put 3 in, I get 1/7 minus 1/9. And then you look, and now the 1/7's cancel. And now if I would continue this process on, however, as soon as you get a term where the first and last terms have canceled, you stop. And you stop, and you will say that the sum is whatever terms in front of that have not canceled yet. When you add them together, is going to be the sum. So here, we're going to get this sum that should wind up being 1/3. Now let's go see if that's the case graphically by looking at the sequence of partial sums in Desmos. All right, so I graph this in to my sequence and series applet here on Desmos. And so we have our explicit formula. Now, if I start and I graph and I look at the sequence itself, notice how the values of the sequence are approaching the x-axis. That's why the nth term test is inconclusive, is because that limit equals 0. Now, we're looking at if the series of partial sums, or the sequence of partial sums, to see if they converge. We said they converge to a value of 1/3. Graphically, if I'm looking here, notice how this graph is getting very flat, whereas I work my way and I start adding more and more terms. Look and see what the sums are approaching. The sums are the y values themselves. So by the time I add 141 terms, I'm at a sum of about 0.3298. And then if I keep going, so let me scroll over here where now I'm looking at, all right, if I added almost 600 terms, I'm at 0.3325, which is getting closer to our value of 1/3. Now that we looked at the graph, since we were able to predict that sum based on that graph, we can say that this does indeed converge because of the telescoping series. All right, let's look at another one here. So this one, I want to know if this series converges or not. So that way I can try to determine what the sum is. We'll do the nth term test, which is to evaluate the limit as n approaches infinity of what's on the inside. So 1/n times n plus 1. Well, as the value of n continues to get larger, I'm dividing 1 by an increasingly larger denominator. This is approaching 0. So according to the nth term test, it's inconclusive. I can't tell you if this converges or diverges. So that means we have to do another kind of test. Now graphically, what I could do is I would go look at this graphically and see if I had access to it and see if the series of partial sums is converging on a value or not. And so if I pull up Desmos here and I have the graph of the plot of the partial sums and I look, we'll notice that the graph of the partial sums, it does level out, and it looks to me like it's starting to converge to a value of 1. So graphically we see that this series is indeed converging. Now let's see how we can actually find the true value of the telescoping series. So graphically, we saw that the series does converge. Now we are saying that we're estimating it to be 1. Now let's show you how to do it. Well, telescoping series, we would expand the series. Well, this doesn't initially look like a telescoping series. So what we would need to do is we would need to do fraction decomposition to rewrite this as two separate fractions. So I'm going to write it as a over n plus b over n plus 1. And I'm going to go through this process and say, all right, get common denominators on the right-hand side. So we have 1 over n times n plus 1 is equal to a times n plus 1 over n plus b times n over, or that's supposed to be n plus 1, times n plus 1. And now we're going to work with the numerators because I want to solve for a and b. And so our method to solve this is called like cover-up method. So we're going to pick values of n that will zero out a term. So if I let n equal -1, that's going to give me 1 is equal to -1 times b. So b is equal to -1. And then if I use n is equal to 0, that's going to give me a to equal 1. So what we have determined is the values of a and b. So I know that a is 1, b is -1, so what I can do is I can make that plus right there become a minus. And so we got these values here for a and b based on these things, the a and b values there. So this is an equivalent form of the expression that we have inside that we're evaluating the sum for. So let's start expanding and writing our terms. So we start expanding, we put in 1 for the n, we'd have 1 minus 1/2 is our first term. And then plus, now we're putting in 2's, we'd have plus 1/2 minus 1/3. And then plus, we put in a 3, we get 1/3 minus 1/4, and this would continue on forever. And we're looking, and we keep going until we get first and last terms to cancel somewhere. So my halves cancel, my thirds cancel. As soon as I get first and last terms to cancel, my sum is going to be whatever is left that has not canceled out in front of that, and that sum turns out to be 1. So it converges to a sum equal to 1. All right, let's look at another one here. So I want to find the sum of the infinite series of 1 over n squared plus 4n plus 3. Well, I need to first do my nth term test. That's the easiest test. It'll tell you right out of the gate if this is going to diverge or not. So the nth term test, I'm going to evaluate the limit as n approaches infinity of 1 over n squared plus 4n plus 3. As the value of n continues to increase, my denominator is getting bigger than my numerator. I'm bottom heavy, which means this is approaching a value of 0. What does that tell us? It basically tells us that we don't know if this will converge or not. So the nth term test is inconclusive. So that means we're going to do something else. What we can do is we can look graphically to see if the series will converge or not. And so graphically, we're looking here at this series of partial sums, and I'm looking, and notice how it gets very flat. And so that means my sum is starting to converge in on a certain value here. And so we're looking, and it looks like the sum, I mean, after we added 639 terms, the sum is approximately 0.4151, which is only minutely bigger than when I added 545 terms, the sum was 0.4148. So we can say that if we were going to estimate that, yeah, the sum would be approximately maybe somewhere around 0.415 or slightly bigger. Now we can agree that this does indeed converge by looking at this graph of the sequence of partial sums. This is not the graph of the sequence itself, but instead the graph of the sequence of its partial sums. So graphically, we just confirmed with Desmos that it does converge. So since it converges, we want to find the sum if possible. Well, I don't have a way to evaluate the sum when it's written in this form. In fact, with this method that we're working on in this video for the telescoping series, I don't really know if it's a telescoping series until I start writing out terms, and I need to get this to look in the form of a fraction plus or minus another fraction. So what we're going to do is we're going to factor this denominator as n plus 3 times n plus 1. And we're going to try to rewrite this in a form where I have a over one of the denominators, say n plus 1, plus b over one of the other denominators, call that one n plus 3. And we go through this process. So I'm going to go through the process of getting common denominators on the right-hand side. So 1 over n plus 3 times n plus 1. is equal to, I would have a times n plus 3 over the common denominator n plus 3 times n plus 1. And then plus my b fraction would get multiplied by n plus 1, which means its denominator would still be that common denominator of n plus 3 times n plus 1. So we're working at this stage with the numerators because I have a rational equation. I want to solve for a and b. So I got 1 is equal to a times n plus 3 plus b times n plus 1. And we're going to do that cover-up method, so I'm going to pick values of n that will zero out one of my constants that I'm solving for. So I'm going to let n equal negative 3. That gives me 1 is equal to negative 2b. So b is equal to negative 1/2. And then I'm going to let n equal negative 1 and solve for a, because that'll zero out my b term. So I got a, or 1 is equal to 2 times a. So a is 1/2. So what we have is we have an equivalent form to write this as a being 1/2. So I have 1/2 over n plus 1. And then minus, since b is negative 1/2, so minus 1/2 over n plus 3. Now I could rewrite this a little bit differently since I have 1/2 divided by n plus 1. If you did skip, change, flip, and write that first fraction would be the same thing as 1 over 2 times n plus 1, or 2n plus 2. And then minus my second fraction would be the same as 1/2 times 1 over n plus 3, or 1 over 2n plus 6. And so this is what I want to expand to see if it's a telescoping series or not. And we're going to start by putting in 1 in for those n's and writing out what we get. So I put in 1 for those n's, and I get 1/4 minus 1/8. All right, and then I go plus, then I put in 2 for the n's. So I put in 2 for the n's. I get 1 over 6 minus 1 over 10. So far nothing is canceled. All right, and I keep going. So I say plus. Now we're putting in 3 for the n's, and we get 1 over 8 minus 1 over 12. And we say, okay, well, we just got our first term to cancel. The negative 1/8 cancels with the 1/8. All right, so let's go do another term. And so my next term, when I put in 4 for my n's, I'm going to get 1 over 10 minus 1 over 14. And I'm like, all right, well, we just got the 1 over 10s to cancel. Now, so far, I haven't had first and last terms to cancel yet, so I got to continue this on one more time. So I'm going to continue this on one more time, and this time we're putting in 5 for the n's, and so we get 1 over 12 minus 1 over 16, and that would continue on. Well, the 1 over 12 I get to cancel, and notice what happens. First and last terms canceled right here, which means that my sum of this series is going to equal all of the terms that have not canceled in front of it, which would be 1/4 and 1/6. So the sum here of this series is going to equal 1/4 plus 1/6, which winds up equaling 5 over 12. All right, we look here at this next one. We want to try to determine the sum of the infinite series from 1 to infinity of 3 plus 2n divided by n squared plus 3n plus 2. And so we're going to do our limit test and say, all right, what is the nth term test? So what is the limit as n approaches infinity of the equation that's here on the inside, 3 plus 2n over n squared plus 3n plus 2? Well, if I look at this, I have an n on the top and an n squared on the bottom. This is bottom heavy. The growth rate of the denominator is much larger than that of the numerator, and so this is approaching a value of 0. You could also see that graphically as you graph this function here. You will see that the sequence of terms will be approaching the x-axis. So the nth term test is inconclusive. So I want to know, well, will this series converge or diverge or not? And so instead of jumping in graphically, let's start looking at let's try to do this without a graph and let's see what happens. So I'm going to have to factor this denominator, because if it's in fact a telescoping series, we would need to write this in terms of two fractions, adding or subtracting from one another. So I'm going to need to take that and write that 3 plus 2n over n plus 2 times n plus 1 as two fractions, one with the numerator of a over that denominator, and then plus a b fraction over, let's say, n plus 1. Now, actually, let's do this. Let's change the order of these so it's n plus, the smaller denominator would come first. All right, so if I go through the process of getting common denominators, I'm going to skip a line here. And so I'd have 3 plus 2n is equal to a times n plus 2 plus b times n plus 1. And then we start solving for a and b. So I'm going to let n equal -2. And I'm going to start solving. So if I let n equal -2, I'm going to get 3 minus 4. So I get -1 is equal to negative b. And so I get b is equal to 1. All right, so b is 1. And we're going to solve for a, so we're going to eliminate the constant b by letting n be -1. So if n is -1, I put in for all the n's, 3 minus 2 gives me 1 is equal to a. So a is 1. All right, so we're looking here. So our series in this case, we've expanded this function to the addition of two fractions. So it'd be 1 over n plus 1 plus 1 over n plus 2. So this is the series that I'm trying to see if it's telescoping or not. And so I'm plugging in n values in here and writing out my terms and seeing if anything will cancel. So we start by putting in 1 for the n's. I get 1/2 plus 1/3. All right, and then I go to my second term. So I put in 2 for the n's. We get 1/3 plus 1/4. And then I put in 3 for the n's. I get 1/4 plus 1 over 5. And then I would do it again. So I get 1 over 5 plus 1 over 6. And now this continues on forever. Now I start looking and I'm like, well, wait a minute. Nothing has canceled yet. And in fact, because I'm adding these two fractions here, in my series I add my terms, nothing will ever cancel. And so by us looking at this, it doesn't look like it's going to converge. So we're going to say that this diverges, and therefore it won't have a sum. Now let's confirm this graphically. All right, so graphically, this first graph we're looking at is the sequence of terms. Notice how the sequence of terms approaches 0. That's why the nth term test was inconclusive. Now if I'm plotting the sequence of partial sums, and it takes a minute, I need to adjust my window here to see and zoom out. Now if I'm zooming out now and we're looking, let me increase the number of terms to see what we have going on. Notice how as I increase the number of terms that my sum is not approaching or converging into a certain value. This here is, I don't see it leveling out anywhere, it just continues to increase on. So graphically, we see that it diverges because I don't see a horizontal asymptote in terms of my terms. And we also saw when we expanded the telescoping series that nothing was canceling, so it wasn't a telescoping series itself.